welcome to the opening ceremony of the 5th International Conference on Mediterranean Geosciences, MED-GU 25, organized by the Department of Geology and Geoenvironment of the School of Science of the University of Athens. The opening ceremony will begin with a welcoming address by the Rector of the National and Kapodistrian University of Athens, Professor Gerasimos Siassos.
Αξιότιμη κυρία Πρόεδρε, αξιότιμοι σύνεδροι, με ιδιαίτερη χαρά σας καλωσορίζω εκ μέρους του Εθνικού και Καποδιστριακού Πανεπιστημίου Αθηνών στην τελετή έναρξης του 5ου Διεθνούς Συνεδρίου Γεωεπιστημών της Μεσογείου, που διοργανώνει το Τμήμα Γεωλογίας και Γεωπεριβάλλοντος της Σχολής Θετικών Επιστημών. Το συνέδριο αποτελεί ένα σημαντικό επιστημονικό γεγονός διεθνούς κύρους. Η Μεσογειακή Ένωση Γεωεπιστημών έχει ήδη καθιερωθεί ως κορυφαίο φόρουμ ανταλλαγής γνώσης, προώθησης της έρευνας και ενίσχυσης της συνεργασίας μεταξύ επιστημόνων από όλες τις υπήρους. Η φετινή διοργάνωση συγκεντρώνει ερευνητές από περισσότερες από 90 χώρες, γεγονός που επιβεβαιώνει την διαρκή δυναμική των γεωεπιστημών σε ένα περιβάλλον παγκόσμιας προόδου, αλλά συγχρόνως και μεγάλων προκλήσεων. Στην Αθήνα, την πόλη που υπήρξε λίκνο της επιστήμης και της δημοκρατίας, οι γεωεπιστήμονες από όλο τον κόσμο ενώνουν τις δυνάμεις τους για να συζητήσουν ζητήματα που αφορούν το κοινό μας μέλλον. Η κλιματική αλλαγή, η διαχείριση των φυσικών πόρων, η προστασία του περιβάλλοντος, η ανθεκτικότητα των κοινωνιών. Θέματα που υπερβαίνουν τα όρια των επιμέρους ειδικοτήτων και απαιτούν συνεργασία και κοινό όραμα. Το Πανεπιστήμιό μας, ως το αρχαιότερο και μεγαλύτερο ίδρυμα ανώτατης εκπαίδευσης στην Ελλάδα και ένα από τα σημαντικότερα της Ευρώπης, υπηρετεί σταθερά την αποστολή της παραγωγής και διάδοσης γνώσης με κοινωνικό πρόσημο. Η παρούσα διοργάνωση εντάσσεται στη στρατηγική μας για διεθνή εξωστρέφεια, διεπιστημονική συνεργασία και σύνδεση της ακαδημαϊκής έρευνας με την κοινωνία. Αξίζουν θερμά συγχαρητήρια στον πρόεδρο της Οργανωτικής Επιτροπής, διακεκριμένο καθηγητή κύριο Παναγιώτη Νάστο, στην πρόεδρο του Τμήματος Γεωλογίας και Γεωπεριβάλλοντος, καθηγήτρια κυρία Σιμίνα Αντωναράκου, και στον κοσμήτορα της Σχολής Θετικών Επιστημών, καθηγητή κύριο Αριστίδη Παρμακέλη, καθώς και σε όλους τους διακεκριμένους επιστήμονες του Πανεπιστημίου Αθηνών που συμμετέχουν για την εξαιρετική αυτή προετοιμασία. Σε μια εποχή που οι γεωφυσικές και περιβαλλοντικές προκλήσεις επηρεάζουν άμεσα την καθημερινότητα των ανθρώπων, η πρόοδος της γεωεπιστημονικής έρευνας αποκτά ακόμα μεγαλύτερη σημασία. Οι γνώσεις που παράγονται και οι συνεργασίες που αναπτύσσονται σε συνέδρια όπως αυτό μπορούν να αποτελέσουν οδηγό για μια βιώσιμη ανάπτυξη σε εθνικό και διεθνές επίπεδο. Καλή επιτυχία στις εργασίες του συνεδρίου.
Presentation of a commemorative plaque to the Rector of the University of Athens by the founder of MED-GU and Director of Publications, Dr. Nabil Khelify. Address by the President of the Department of Geology and Geoenvironment of the School of Science, Professor Asimina Antonarakou.
Dear Rector, dear guests, dear colleagues and friends. On behalf of the Department of Geology and Geoenvironment, it is my great pleasure to welcome you to the National and Capodistrian University of Athens and to the 2025 Mediterranean Geosciences Union Conference. Our department has had the privilege of coordinating its organization, and we are honored to bring together such an outstanding community of geoscientists from across the Mediterranean and beyond. The challenges we face today, from climate change and environmental degradation to resource scarcity and natural hazards, remind us that the Earth system is deeply interconnected. The Mediterranean, a cradle of civilization and a hotspot of environmental change, is particularly exposed to these transformations. Understanding its complex dynamics requires collaboration across disciplines, nations, and perspectives. Through its many sessions covering topics from geohazards and geoinformatics to energy, geomorphology, and climate and beyond, Mezgiu 25 brings us together to exchange ideas and to find ways to apply science to real environmental challenges. As hosts, we hope this meeting will strengthen the professional and personal ties that make our community so vibrant. I encourage you to exchange ideas, explore new collaborations, and get inspired by fresh approaches to the challenges our region and planet face. Once again, welcome, and I wish you all a productive and inspiring conference, and thank you for being here.
Address by Professor Panagiotis Nastos, Department of Geology and Geoenvironment, School of Science.
Dear Rector, dear President of the Geology Department, distinguished colleagues, esteemed members of the Mediterranean Geoscience Union, honored guests, dear friends, it is a great pleasure and a deep honor to welcome you all to the 5th annual meeting of the Mediterranean Geosciences Union, Mezgiu 2025, here in the historic and inspiring city of Athens. On behalf of the National Capodistrian University of Athens, which proudly hosts this year's meeting, and the Mezgiu board, I extend my warmest greetings to everyone joining us, both here in person and online, from across the Mediterranean and around the world. This gathering marks an important milestone in the journey of Mezgiu. It reflects our shared commitment to advancing geoscientific knowledge and to strengthening collaboration across nations, disciplines, and generations. Since its creation, Mezgiu has become a true home for interdisciplinary research, uniting Earth, environmental, and planetary scientists who work together to understand and protect our planet. And where better to hold such a meeting than Athens, a city where scientific curiosity was born more than 2,000 years ago? Here, ancient wisdom meets modern innovation. The same spirit that once asked why the Earth behaves as it does continues today in our universities, our laboratories, and our field studies. The theme of sustainability lies at the very heart of this conference. We gather at a time when the Mediterranean region, and indeed our entire planet, faces the growing impacts of climate change. Rising temperatures, water scarcity, land degradation, and extreme weather events remind us daily that our research is not abstract. It is essential for society, for the environment, and for the generations that will follow. As Mediterranean scientists, we share more than geography. We share a common sea, a common climate, and a common responsibility. And through Mediterranean collaboration, we can turn shared challenges into shared solutions. Mezgiu stands as a symbol of that cooperation, a bridge between scientists, between continents, disciplines, and communities. Only by working together, linking geology with climate science, hydrology with urban planning, geophysics with renewable energy, can we develop the holistic understanding needed for a sustainable future. Over the next 3 days, we will enjoy an exciting scientific program, keynote lectures from distinguished experts, specialized sessions covering every corner of the geosciences. Let us use this time not only to exchange ideas, but also to build friendships and collaborations that will continue long after the conference ends. I wish to express my heartfelt thanks to the Mezgiu board for their vision and dedication, to all our partners and sponsors for their generous support, and especially to my colleagues at the National and Kapodistrian University of Athens for hosting and organizing this event with such enthusiasm. To our keynote speakers, conveners, and volunteers, thank you all for your hard work and commitment. Dear colleagues, as we begin Mezgiu 25, let us remember that science is more than a pursuit of knowledge. It's an act of service. Through our work, we serve humanity, we serve our environment, and we serve the future of this remarkable region we call home. Welcome to Athens, welcome to Mezgiu 2025, and may this meeting inspire new ideas, new collaborations, and renewed hope for a sustainable Mediterranean and a sustainable world. Thank you very much.
Address by the President of Mezgiu and Head of the Mezgiu Publications Committee, Professor Attila Tsiner.
Okay, good morning, welcome everyone. My name is Attila Tsiner and I'm from Istanbul Technical University, Eurasia Earth Science Institute, and president of the Mezgiu. I would like to talk about a little bit the history of this meeting that we are celebrating the 5th today. So let me check how this advances. Okay, we did the first Mezgiu in 2001, just after the COVID pandemia in Istanbul Technical University. And this was a first meeting, but we had more than 200 people and around 100 people online attendees. And we did this in a Humboldtian spirit. So we wanted to create this Mediterranean Geoscience Union for people all around the Mediterranean. Although today it became more universal, our first target was the Mediterranean area. And after the meeting, we did a really nice field trip in Cappadocia region that we might one day maybe organize the conference there as well. And the second meeting was in Marrakesh. This was also really an excellent event with field work at the end and with many people from North Africa attending, as well as from Europe. The third one, again, it was in Istanbul for some practical reasons. So this was our third meeting, and the fourth and the last one was organized in Barcelona, where I am now on sabbatical leave. And this was a major event, so we attended around 400 on-site participants, and later we did a nice field work in the Pyrenees, in all Spanish, French, and Andorra Pyrenees for 3 days. And it was a really nice event. And for the last time, I would like to thank to my dear colleague, Celal Şengör, who he's our honorary president, let's say, and this is his slide, not mine. He came up with the idea that Nabil Kelifi, who is the founder of this union, and myself as president, and I am also editor-in-chief of the Mediterranean Journal. What was the name of the review? Okay, Mediterranean Geoscience Reviews. This is the journal that we publish since 7 years. So I invite you to check this and submit your papers. This is a Scopus index, and soon with Web of Science indexation. We publish articles, review articles, or normal regular articles related to Mediterranean, but not only. If the subject is interesting, we publish from globally. So the idea of Mediterranean Geoscience Union, to begin with, it was actually to promote this journal, and I'm doing just that now. And I expect that, I hope that you will decide to submit to this nice journal. So once again, I would like to welcome all of you to Athens, and I would like to thank especially to the local committee with Panagiotis Nastos as the professor. He is the local chairman and local president of the Mezhegu, and to his committee. So enjoy this beautiful city. Although it's raining today, it will be much nicer afterwards. And enjoy the science and Athens. Thank you very much.
Address by the founder of Mezhegu and Director of Publications, Dr. Nabil Kelifi.
Yeah, so welcome, dear colleagues. Very, very happy to see you, many of you again. And there are also new colleagues joining us, joining the Mezhegu community. So I hope it will be a fruitful experience and good conference for collaboration to enjoy the city and to build new projects together and also to publish with us. I'm happy to see you here in Athens, and my presentation will be very short. Well, I will give you some key points about the Mezhegu. Of course, I would like to start to thank the director, the president of the university for hosting us, for joining us today, and our local president, local chairman of the Mezhegu, Professor Nastos, and his colleagues from the department, and the head of the Faculty of Science. She's also here today, and our plenary speakers and all of you. So thank you for joining us for this 5th Mezhegu. Yes, I will go through the colleagues who helped me to establish this idea, and as Attila, he said, 2021, so thanks to them, this project has developed and now is attracting attention, and scientists, very good scientists we have each year, they join us, so we are proud of that. Those are our advisory committee. Perhaps you know that Professor Thibault is one of the AGU founders, yeah? And many others. And of course, our local organizing committee here in Athens, led by Professor Nastos, the Faculty of Science, Department of Geoscience, they are the organizers of this Mezgeu. And of course, our program committee with Professor Maghraoui, I hope he's here with us. I think he will join, of course. And the publication committee, very good scientists that they are really helping us to evaluate the abstracts and then the proceedings papers. There is also our technical committee. The conference is divided into tracks to try to cover all fields of earth science. And each track is led by a chair of those tracks. So they are the ones who control the quality of the abstracts and the proceedings. So we have many tracks, as you can see here, from geoinformatics to hydrology and sedimentology, stratigraphy, etc. Yes. And also this year, we, like every year, we open the call for special sessions for those who have ideas for hot topics to be discussed. And this year, it is really good. We are really happy to see that many special sessions, they were really successful. They attracted many submissions. And I suggest you to attend many of those special sessions. They are really tackling new hot topics. So it is really good to attend those special sessions because they are led by experts in the field. So it is a good opportunity to meet those people and discuss with them. Yeah, just an overview of the Mezgeu this year. Yeah, many countries, as usual, more than 70 they submitted, authors from those countries. And our editors, the proceeding editors from the technical committee, they helped us to evaluate, and the acceptance rate was around 60 to 65%. Yeah, of course, not always easy for, even if you accept someone, it is not easy to come. I know it's challenging. First, perhaps there are some financial issues, or we heard a lot of problems of visa. So we tried to help. Professor Nastos, he was really in touch with embassies worldwide to answer their questions. Our Mezgeu office always answers questions, but it is not easy for those. We are really, we apologize that they are not with us today. Yeah, so Mezgeu this year attracted over 510 compared to 700 last year in Barcelona. But still, we are happy that many people are still coming and joining. And yeah, I think the problem of visa has reduced the number. And we will, with Professor Attila Chiner, we will continue the evaluation of the proceedings, hopefully this year, and his co-editors, hopefully this year will be quick in the evaluation. Always we publish in indexed, in a Scopus indexed series with Springer. This is the conference program. I think we send you the link, so please try to use it. It will help you to really move through rooms, from room to room easily, and to know where to go. This is the main building. After this, we will not use it until the closure, but there is a room to the right and a room to the left. And then outside, it is raining, sorry, but I hope in the afternoon it will stop raining. So on this web app, you can browse through the program and so on. And as I said, those are the rooms. I will explain later how to navigate. Yeah. There are other rooms, and if you go to this web app, there are the links that they lead you to Google Maps, so to find your way easily. It is in a walking distance, I think maximum 5-8 minutes, some rooms. But the majority, the most of the rooms, they are centered around us here. This is the map. We have changed the map, so what you have in your bag, I'm sorry, there is a last-minute change of room, so please follow the email. We sent you the same brochure here that shows the exact map with links, as I mentioned, yeah? Yeah, those are our tracks, our tracks of focus. Majority of participants, it is equilibrium there between doctors, professors, and students. Many students, they join us. I know they have sometimes not easy to get funding, but there are many here today, which really makes us happy to see students because they have the new data. It is an opportunity for them to present at an international event where scientists, good scientists, experts, they come to them and discuss. I remember those moments are important when I was a PhD student. So please, the senior scientists, give attention to those juniors and try to discuss with them, ask them questions, and show interest to their work. Yeah, this is the repartition by track. As usual, we receive most of the contributions from Algeria, so always from Algeria. This year is less. Morocco, of course, Greece, the host, and Italy, Turkey, as usual, Spain, Tunisia, France, and all Mediterranean and some neighboring countries. So 78 countries. This is our plan for publishing. You'll find it on the website. Many of you criticize us of being late. You know, we have around 600 papers, and they should all be published together. And sometimes they are divided into 6 books or 5 books. And you know, they don't have all the same quality, so we should, even if someone he has been accepted, we should wait for the others until we reach an acceptable version of their papers. So please, your patience and your understanding. I know scientists, they don't like to wait in publishing especially, but please remember it is a book. It is not publication in a journal. So there are several books, and they need some time until we fix everything, yeah? So this is the link of our conference on Springer website, where you find the proceedings. And yes, 2023 published, and all the others, 2022, 2021, but I'm mentioning 2023 because it was recently published, sorry. Yeah? And now we are in progress with 2024 proceedings, and for this year we will do all of our best to catch up in the delays and try to finish in a good time. But if you go to this link, you will find your work in the future, yeah? Or if you have published it with us in the past. Yes, as the editor-in-chief of this journal, which I approached him 7 years ago to publish this journal, we are planning to publish at least 1 special issue. If you have proposals, you can send it to them or to the Mεσογείου office. You have the email. I think you will be happy to discuss your proposals. I know some scientists already, they will publish special issues. So, yeah, the icebreaker this evening, it is a very nice walk from here to that place. You will find it on the map. But the weather is not good, so I hope we can walk there. Everyone is invited, free of charge. I think it is 20 minutes walk or 10 minutes. 10 minutes walk. I took 20. Yeah, we'll go up. Yeah, okay. Then the gala dinner, it is paid event, but if you would like to join, there is still possibility to register today. For the gala, there is music, dance, very nice food in this famous Royal Olympic Hotel. If you would like to join us. I think already 80, they already will come. On this occasion, I would like to invite the director to join us and the head of department. So they are welcome, Professor Nastos, to join us, please, to this event, to close the Mezgeu on Wednesday. And then we move together to the dinner, if you have time. Thank you. Yes, on Thursday, after the conference, we'll go for the famous Meteora and Delphi UNESCO World Heritage Sites. We'll move from here. We are now around 18, and there is still possibility that you join us if you register and pay today. So it will be a 2-day in a nice hotel there, Delphi and Meteora, and yeah, this is the plan, 13, 14 November. We'll come back here to Athens at 7 p.m. on the 14th of November. Yeah, so thank you very much. The idea is bridging this north-south gap in everything, not only science, in relationships, in friendship. So we are closer from the northern shore of the Mediterranean, southern shore of the Mediterranean. We have a lot of common culture and science to share. So hopefully that the science that you will produce will serve the society, the Mediterranean and beyond. Thank you very much. Because it is raining, the plan was to make a group photo outside, but we will do it here. So shall we do it like that? Well, they see from here and then you go up. And later, I'm sorry today, normally Mezgeu always starts with a nice coffee break. Professor Nastos, are they coming or not? Or because of rain? No? Risky. So after the photo, the keynotes, they will start, and I hopefully during this time they will provide coffee. Yeah? But for sure there is lunch, yeah? Light lunch. We go there? Yes, okay. Please, can you join us just here to make a nice photo? We'll send it to you after the conference and with all those photos, yeah? I can do it. Yes. What is my photograph?
Please do join us here for the photo. All of you, please. Thank you.
Director of Research at the National Observatory of Athens. So, the first speech. So, the next speech is by Dr. Christos Giannakopoulos, Director of Research at the National Observatory of Athens, IPCC National Focal Point, EU Horizon Mission Adaptation National Representative.
Thank you for the invite. I'm going to present you some recent work that was done at the National Observatory of Athens together with my colleagues. Most of them are here today. And this work is called High-Resolution Gridded Datasets for Greece, from daily observations to downscaled climate projections. So the aim is here to create some gridded observational and climate projections datasets specifically aimed for the territory of Greece. It is a methodology that can easily be followed to other countries and other territories, so it is an easy methodology to follow if you want to obtain high-resolution datasets for specific regions or countries. What are the challenges behind this work? The high-resolution climate information is an essential component of a country's comprehensive framework for responding to the risk of climate change and for the implementation of adaptation policy and strategies. So it is very important if you want to have a comprehensive adaptation strategy and to do climate change impacts for various sectors, to have very well-defined and high-resolution data sets where you obtain your information. So in order to do that, you need definitely high-resolution, both observational timescales and climate projections. The available state-of-the-art climate change modeling experiments coming from the IPCC, the CMIP6 experiments, have a horizontal resolution of about 100 kilometers, and this resolution, of course, is to support adaptation planning or decision-making at local and regional scales, especially in the country of Greece, which is a very complex topography and territory, and the local climates of the country are very highly variable due to the complex topography. So this project called Climadat Hub aims to bridge the gap between available climatic information and information required for assessing climate risks at local scales. It is a 2-year project. The coordinator is the National Observatory of Athens, where I work. It is implemented in the framework of the Hellenic Foundation for Research and Innovation for basic research financing under National Recovery and Resilience Plan. The specific objectives of Climadat Hub is to include the development of state-of-the-art 1-kilometer daily gridded observational datasets for temperature, precipitation, relative humidity, and wind speed. And the time frame here is 1981 to 2021. And for climate change projections is similar to obtain 1 kilometer statistically downscaled climate change projections. All this information is going to be presented and placed in a public repository for the produced datasets that will be one-stop shop for high-resolution climate data for Greece. So everything will be made public and everything will be placed in a public repository. These robust climate data can be easily, of course, utilized by stakeholders and decision makers to develop well-informed, science-based local and regional adaptation plans and to allow better use of water resources or to improve agricultural production and sustainability, or to make urban areas more climate-proof. Where we obtained the sources of information, the observational data for precipitation we got from the Ministry of the Environment, from the National Hellenic Meteorological Service, and from the National Observatory of Athens for various years that they had observational data. The sources for temperature, relative humidity, and wind speed we got from the National Met Service and from the National Observatory of Athens. For the station data, we did, of course, some post-processing of the observational data, which included quality control, gap filling, and homogenization. And for precipitation, we took only the stations where they had less than 10% of missing data. For temperature, relative humidities, and wind speed, we reconstructed missing values using a methodology of a published paper and using the ERA 5 land dataset, gridded observational dataset. Here is the density of the stations that we got for precipitation with red dots in the map. And the right map shows the density of the stations that we got for temperature, minimum temperature, average temperature, maximum temperature, relative humidity, and wind speed. We did, of course, some gridding techniques, and the methodology selected to interpolate daily temperatures and daily precipitation sums is the one that was used in the EOBS dataset. This is a well-established gridded observational datasets covering most of the European territory, and Iberia 1, which is a dataset that has been used to create a similar database for the Iberian Peninsula. The steps to obtain the daily values of the gridded datasets was interpolation of the monthly values and the daily anomalies. The interpolation of the monthly values was applied to the monthly values, considering also the elevation as a covariate, and the daily anomalies with respect to the monthly values was interpolated using the ordinary gridding method. The two steps are added in terms for precipitation, relative humidity, and wind speed, and multiplied when we do the precipitation. Of course, besides the fixed rank rigging that I mentioned that was used and decided that we take this method, we tested also other interpolation methods like generalized addictive models or nearest behaviors or support vector machines. But we found that the FRK, the fixed rank rigging, was better suited for robust precipitation interpolation across the regions of complex topography. This map shows you all the methods, and you can see from the statistics that the FRK was superior. In addition to the methods presented before, we added a little bit of dynamics in our procedure. So we used also WRF simulations, which is a dynamic model, for 1 year of runs as a spatial interpolator in order to construct daily gridded temperatures of maximum, minimum, or average temperatures, relative humidity, and wind speed. The temporal alignment, for temporal alignment, the WRF outputs, this model, are perturbed with interpolated monthly variables to match long-term observed climate while preserving the spatial variability. And for bias adjustment, the perturbed WRF outputs are transferred to the gridded dataset using unbiased bias adjustment methods, ensuring corrected daily scale representation. And this is the dataset that we get for the present period. We have the different variables here. The top left is maximum temperature, then we have average temperature, then we have minimum temperature. And the bottom we have precipitation, relative humidity, and wind speed. And you see how Greece is represented in terms of temperature, relative humidity, wind speed, also precipitation. It's important to see that for precipitation, the map shows correctly the west to south, the east-west divide of Greece, with more rainy part in the western side and more dry part in the east side. Then we compared our dataset, what we produced, with a well-established dataset in the bibliography. And this is the CHELSA dataset. It's a global land dataset providing daily air temperature, precipitation, and solar radiation at 1 kilometer resolution. This dataset is from 1979 to 2016. And we used this because they use the same digital elevation model, so they have a common grid, and consistent elevation values across points. And a recent publication in Greece, they found that CELSA is one of the two most reliable gridded datasets for describing precipitation dynamics in Greece. The evaluation matrix that we used was the bias, root mean square error, mean absolute error, and Klein-Gupta efficiency. And this is a comparison between our dataset and the CELSA dataset. The left side is our dataset, the right side is CELSA dataset. You can see here the plots for the annual average temperature and the plots below for the summer maximum temperature. And you can see that our statistics are much better. So we have comparable results, of course, but our datasets is having superior spatial performance and closer agreement with observations for the average values. Continuing for metrics such as summer maximum temperature or summer days above 35 or tropical nights, we see that again they have comparable results, but our datasets, the Clima.grid datasets, demonstrate superior performance, closer agreement with observations for extreme values. Especially for the summer days above 35, you can see that our datasets very well represents the thermal hotspots in Greece and captures as well for the tropical nights the urban heat island effect, which is very evident for the Attica Peninsula and the city of Athens. In terms of precipitation, our dataset, the Clima.grid dataset, here we show an example of winter precipitation, shows higher precipitation than CELSA, but with negligible variables against observation, where CELSA has larger seasonal bias. Both, of course, capture the west-east gradient, with differences, of course, more evident in our dataset, especially during the rainy season. You can see here, for example, the west part of Crete that shows more rain in comparison to CELSA, which appears a bit drier. Then we proceed a similar methodology to do for climate projections. Here we used a sub-ensemble of CMIP6 models for Greece. The models that we used here are mentioned below, 4 models. We used 3 different climate change scenarios. One was the very optimistic scenario, SSP 2.6. We used also the average scenario, SSP 4.5, and the extreme scenario, SSP 8.5. Statistical downscaled is performed using the methodology that we followed in the previous examples, so regridding to the Clima.grid and apply a bias adjustment using empirical quantile mapping techniques. Here the results that we get, and you can compare the present period on the left plot and the different future periods on the right plots with the 3 different scenarios. This is the annual maximum temperature, and you can see how much more increases we have in the annual maximum temperature as we go to the average and the extreme climate scenarios, the 8.5, and as we go further into the century, 2081 to 2100. Also, the same is very clear with the number of days above 35. You can see how many more days we are going to have in Greece in the distant future, in 2021, if we go with the pessimistic scenario, with the extreme 8.5 scenario, you can see that you can have more than 120 days per year with temperatures above 35. That means 4 months per year with temperatures above 35 in specific locations in the country. Same is happening with the average annual temperature, significant increases. And the same is true also for tropical nights. That means nights that the temperature doesn't fall below 20 degrees. And you can see, if we go with the extreme climatic scenario, we are going to experience more than 180 in areas of Greece, so 6 months per year with temperatures at night not falling below 20 degrees centigrade. In terms of precipitation, there is a variable picture. Not all scenarios show decreases of precipitation, but the scenario 8.5, which is the business as usual or the pessimistic scenario, shows significant decreases of precipitation that are more than 10%. Also, changes you can see also in the number of maximum one-day precipitation, which is a metric that we use to identify extreme precipitation events. And you can see some changes here, how many millimeters are going to be falling in one particular day. Not more, some increases are projected here, which is not a very enthusiastic conclusion. And as a summary, I can say that the ClimaDat grid that we created is the first publicly available climate data set for Greece that covers observational period 1981 to 2021 at 1 kilometer resolution, is built from homogenized data set using 122 stations for temperatures, relative humidity, and wind speed, and more than 300 stations for precipitation. This publicly available data includes temperatures and precipitation for period 1991 to 2018. You can find in Zenodo here is publicly available. And future projections and more of a current climate at 1 kilometer will be available also publicly at the ClimaDat Hub repository by the end of this project. Thank you very much for your attention.
Could we call Professor Nastos? So we can call Professor Mazarakis to give the certificate of So the next speech is by Mr. Derek Ellsworth, Professor at the G. Albert Shoemaker Chair, Professor of Energy and Mining Engineering and Geosciences, and co-director of the Center for Geomechanics, Geofluids, and Geohazards at Penn State University, USA.
Thank you very much. Thank you very much. It's a pleasure to be here. It really is a pleasure to be here. Thank you. I arrived yesterday. My bags didn't follow me, but they should be en route now. So as you may know or may not care, apparently in the US we don't need a federal government at the moment, and they've been out for 40 days. And air traffic controllers are now getting weary to turn up, and so that's why the air I worried that I would actually get here. I recorded this talk and left it on my website just in case, but actually I managed to make it. I see the screens are very small, so I will use them as prompts to be able to have more of a conversation about what's going on. The talk today is about linking natural seismicity to determine permeabilities in the crust. Permeability is, of course, the mechanism by which fluids get cycled and elements get cycled in the crust. It's the mechanism by which we're able to remove energy fluids and fuels from the crust, and so it's an important parameter. And of course, in some cases, we inject fluids under pressure for hydraulic fracturing or hydraulic stimulation of deep geothermal reservoirs, and we know that those create seismicity, and we do it specifically to create permeability. And so maybe there's a linkage between the seismicity that occurs and the permeability that results from that in the natural world. So I'd like to try and explore that today. The distribution of permeability in the crust is very steep. It decays very quickly with depth. This shows permeability as log permeability decreasing with natural scale of depth. And as you see, it goes from relatively large magnitudes near the surface to very small magnitudes at depth. And this, of course, is a balance between agents that create permeability, earthquakes being some of them, and those that destroy it by chemical means, by the sealing of fractures that are produced. If you look at the geological evidence for this, these are some observations from a well in California, looking at water levels in the well driven by earth tides, the passing of the moon and other celestial bodies around the earth. You can show that when you get far-field earthquakes arriving, the vertical dashed lines in these plots, relative to the predictions of permeability, the dotted blue lines and red lines, you get a sudden increase in permeability that then decays until the next earthquake and then repeats at the time of that event. So that suggests that there is some impact of far-field earthquakes, at least on permeability. If you look at using machine learning to increase the number of picks you get from natural seismicity, these data from Southern California on the San Andreas Fault, you see that you can observe fluids migrating in faults, not necessarily changing permeability as they migrate, but being as a marker for that migration. And the same behavior that we saw naturally in the 2 slides ago in California, where you get an increase at the arrival of an event and then a decrease over the interseismic period, is that you can see that behavior also in the laboratory, where you get a destruction of permeability in the interseismic behavior before the next period. So we see some evidence of a linkage between earthquakes and the evolution of permeability. And of course, we'd like to be able to use microearthquakes, maybe, to be able to say something about that direct profile without having any information about the permeability itself. So maybe to do that, we have to know a little bit about the mechanisms by which earthquakes form. We know that with induced seismicity, when we inject fluids to make permeability, we can reactivate faults by the large pore pressures that we generate that reduce effective stresses and cause faults to slip. And that's relatively well understood. We don't understand it well enough sometimes to control it, and so there have been a number of instances, one in Europe, the Basel EGS Deep Geothermal Project in 2004, which was shuttered because of a magnitude 3 earthquake, and the Pohang earthquake in South Korea in 2017, which had a much larger 5.5 event that resulted from an attempt to generate permeability in that reservoir, and also, as a result of that, shuttered that project also. In general, the size of the events, the magnitudes of these events, are linked to the amount of fluid that's injected, because that controls the magnitude of fluid pressures. And you can link that behavior through this relationship where seismic moment, the energy from an event, is proportional directly to the volume that's injected, because that is a proxy for the large pressure that's results. And the Pohang earthquake, the red star in this plot, plots way above this norm for the magnitude defined as the product of the volume injected and the shear modulus G of the the reservoir to be. And the question is, why is that? You could make the case that that is because in the earthquake cycle, you build up tectonic stresses, very dramatic. You build up tectonic stresses almost to peak strength, and then as you go over that strength, you get a large stress drop. But as you build up, and if you're resting at a relatively high pre-stress already, a small amount of drop in strength due to injecting a small amount of fluids will be the straw that breaks the camel's back that will induce a large event. And so you can show that by making laboratory earthquakes, where you pre-stress a laboratory fault, you inject fluids to be able to bring it to failure, and you measure the seismic moment that results from that. And on the right-hand figure, you see some laboratory data in orange in the lower left-hand side, and the field data on the right-hand side. And they basically show that as you slowly increase the magnitude of pre-stress, you can indeed get a very large event for a very small volume of fluid that you inject. You can codify that by looking at scaling the pre-stress to maybe 70, 80, and 90% of the strength before you start injecting. And indeed, you see as a result of that, in a quantifiable way, you can induce relatively large events for very small injection volumes. So the theory holds that that might be a reasonable hypothesis for why we get relatively large events. So if we want to link permeability to seismicity, what are the other controls that condition the magnitudes of an event? We know that if we want to generate a large event, this region is not immune to those. The Gulf of Corinth in Greece, also the Anatolian Fault in Turkey and Syria from 2 years ago now, is that if you want to have a large earthquake, you can't do it on a very small fault. And so the size of the fault scales also with the size of the event, which means that if you have large events, the largest induced events that we know of, maybe in the US and also in Europe as well, are the order of magnitude 6, 5.8 on this figure. And to get an event that size, you need a fault which is kilometers or larger in scale. We also know that earthquakes, induced and natural earthquakes, come in two different flavors. They come as the regular earthquakes, which eject their energy maybe in 90 seconds or 2 minutes, which we know as earthquakes. But they also come as silent earthquakes, which eject the same amount of energy, but maybe over months to a year, and therefore are much less destructive because the energy release rate is so much less. And so we also know the mechanisms by which we can move between these events. It's related to the role of the stiffness of the loading system, which controls that. So to get an earthquake, we need three basic requirements. We need to take a fault to failure, either by raising tectonic stresses to those magnitudes that it fails, or by injecting fluid pressures that reduce strength and cause it to fail. When it fails, it has to be velocity weakening, so that as it displaces, it becomes weaker and weaker. If the converse is true and it becomes stronger, it will automatically self-arrest. And the final, but more esoteric requirement is that the loading system, the stiffness of the loading system, has to be softer than the fault itself. And that is that the loading system has to be able to eject all of the energy, the stored energy, into the fault for it to then radiate outwards and cause the damage that we know. And this third criterion, the stiffness, can be linked to these behaviors, but it requires that this velocity weakening behavior is present. And so we can link this stiffness somewhat esoterically through that, but we require that this A minus B parameter, which defines that the fault will progressively weaken as it displaces, has to be decreasing with velocity. We see this in field experiments. So earthquakes are difficult to monitor because we don't know where they'll be, we don't know where they will come. But if you make your own earthquakes, small in situ earthquakes, then you know that you will be in the right place to be able to capture them. And this is an experiment in actually in Europe, in a former ballistic missile base underground in France, the LSSP, in carbonates, where within a borehole, packed off section, fluids were injected to be able to remobilize a fault and to create a very small earthquake. And in this behavior, what occurred was that as the displacement occurred, the initial displacement was aseismic. There was no seismicity that was apparent, shown in red on the right-hand side. But as the patch that was being inflated by the fluid pressure that was injected got larger and larger, all of a sudden the fault became seismic as it slipped. And so this is a manifestation of the fact that the stiffness of the fault, which is related to its length, as you make a longer fault, the geometric stiffness of that fault becomes lower, softer, and therefore is able to transition to be seismic rather than aseismic. So maybe we can use this idea that the fault loses its strength or gains strength as a proxy to be able to talk about styles of deformation and therefore styles of permeability change. For the creeping fault, we generate porosity very slowly, and we destroy porosity by creep as quickly as we generate it. But for dynamic rupture, this velocity weakening in behavior, we do the converse. We create porosity very quickly, much more quickly than we destroy it, and then maybe we can use that as a proxy to define permeability magnitudes. So if you do experiments in the laboratory to shear laboratory faults, measure the characteristics of their velocity weakening or strengthening behavior, the left and right-hand sides of this graph, and we also measure the changes in permeability that the fault goes through, whether it increases or decreases as we shear it, then maybe for creeping faults that get stronger, we'd expect to fill the bottom right-hand quadrant of this, and for dynamic faults that create porosity much faster than we destroy it, we perhaps would expect to populate the upper left-hand quadrant, increasing permeability for brittle failure, decreasing permeability for ductile failure. It partly conforms to that, but not particularly strongly. There are lots of false positives. We see this for other locations as well, the same behavior, lots of false positives in the upper right-hand region. So maybe that's not quite as useful a technique to have as we could do. So maybe there's an alternate way to do that. One way is that we could use, if we have observations of permeability and of seismicity, which aren't very frequent, we could use that information to look for patterns in that behavior. They don't occur very often. We have lots of measurements of seismicity, both induced and natural, but we very rarely have measurements, in situ measurements of permeability that go with them. But there are a couple of occasions here where we actually do have permeability records that are measured. This site is in Utah. The box on the left-hand side in the picture of the US is Utah. It's the Frontier Observatory for Research in Geothermal Energy, the acronym. And it is a stimulation project at about 3.5 kilometers, where the reservoir is being created, porosity is being made by injecting fluids, and as a result of that, generating seismicity as well. So in the same place, we have seismicity and the magnitudes of the permeability that is generated by that seismicity. So these are step tests. The blue curve represents the stepping up of flow rates. The red represents the increase in wellhead pressure that goes with it. The blue curve underneath it represents the ratio of flow rate injection to pressure, the so-called injectivity. And that's kind of a measure of the permeability. Not quite the permeability, but it's a proxy for permeability. But the problem is that when you stop injecting, the injectivity goes to zero. And of course, permeability that you've made won't quite go to zero. And so we want to be able to convert that into a magnitude of permeability. So what we could do is we could think about injecting fluid at the wellbore, defining the exterior of the microseismic cloud and anticipating that the fluid pressure goes from that injection pressure to the background pressure at the edges of that microseismic cloud, in which case we can write an equation that allows us to define the permeability change of that system. And so that's the bottom curve here in blue, the magnitude of permeability that ramps up to a peak and then stays at that plateau once we've created it. So at this particular site, there were 3 different stimulations. One was injecting slick water, water with friction reducer. One was injecting water with propant in it to keep the fractures open. And one was injecting water with polymer added to be able to do that. So we have 3 different stimulations, 3 different sets of data. And so we'd like to be able to look for patterns between the observed microseismicity at these sites and the changes in permeability to be able to see if there are patterns. They don't seem very obvious to the naked eye, but what you could use is machine learning to be able to train the data sets for the observed permeability changes with the observed seismicity, so that ultimately, after you go through training, evaluation, and finally testing, you use the observations of microseismicity to guess, to estimate the magnitudes of permeability where you don't know them for that particular stage, in stage 3. And so these are those results. The first left-hand figure is training the data where we know permeability and the seismicity that caused it, and we can develop statistical relationships between those. But the right-hand curve is where we don't know what the permeability change is in red, but we predict it merely from the cumulative seismic moment in blue that we've measured at that particular site. And we get a reasonable magnitude for that. We can use other locations. This is an underground research lab in the central part of the US, in South Dakota, not North Dakota. And it's an underground physics lab for neutrino physics, similar to CERN, but CERN, of course, is not at depth. So in Europe, it's similar to Gran Sasso in the Apennines in Italy, or in Canfranc in the Pyrenees in Spain. And the idea here in the bottom right figure, you can see in gray a tunnel. And from that tunnel, there are 2, an injection well bore and a recovery well bore in green and red, and fans of boreholes that go above and below those, which define places where you can measure the seismicity. So at 1,500 meters of overburden depth, you can generate microearthquakes by injecting fluids and measure the permeabilities that result from them, but also get very close to those magnitudes by having your monitoring points maybe only 15 or 20 meters away from the injection site. And you get exactly the same sequence of behaviors as before. You have stepped injection rates, the pressures at the wellbore that result from them. You can take the ratio of those to get injectivity in the second plot down. If you look at how far the seismic cloud has gone out, that gives you some boundary conditions to calculate permeability. And then in the bottom plot, you have everything you need. We have cumulative seismic moment, we have the seismicity rate, and we have the evolution of permeability that results. We had 5 episodes of injection in that particular case. The first 2 were very quiet, so there's no information coded on the permeability in those particular cases. But using the 3rd, 4th, and 5th episodes, we can do exactly the same as we did before, using machine learning to be smarter than we are and look for connections between the 2 data sets. And again, you get the same behavior. The left-hand figure is training it to be able to look at the recover statistical correlations between the seismicity and the change in permeability. And the right-hand figure is predicting the permeability only using the microseismic records for that particular injection episode. And you see it performs reasonably well. So we have 2 sites where we've done that. Is there a universal law that links this somehow? Well, what you could do is you can use so-called transfer learning. You can train the model based on the forge data, in this particular case, on the left-hand panel, and use the earthquakes at CoLab on the right-hand panel to predict the behavior of permeability at CoLab. So train with forge, but apply collab data to see if you recover the collab permeability. And you do. You can do the converse to train it on the collab data in South Dakota and make predictions based on the earthquakes in Utah to predict the permeability in Utah. And again, you see that you get some reasonable results out of it. So the question is there something that's generalizable that says something about the fundamental relationship that links them? EGS, Collab, and Forge are something like 1,000 kilometers apart, completely different structural regimes. But in each of these field data and lab data, we see that when you shear fractures due to an earthquake, they dilate. And as they dilate, they create porosity. And that porosity is also registered as a change in the permeability. So the fact that we're able to predict permeabilities from the cumulative seismic moment suggests a relationship. If we can link the permeability to the change in aperture of a fracture, which we can, delta B in this figure on the left-hand side, then that's useful. If we can link delta B to the shear displacement of the fractures and the dilation that occurs as it ramps up over the roughness, that allows us to link a change in aperture to the shear displacement. And if we can link the shear displacement to the magnitude of the earthquake that drives it, then we have a linkage between the magnitude of the earthquake and the change in permeability. And so we can rationalize, in this particular case, don't worry about the math, that permeability change should be in some way proportional to the cumulative seismic moment. So if we want to further investigate that, so we have two sites where that works. It works for both of those data. Maybe we can do some experiments in the laboratory to constrain it by doing exactly the same. You generate earthquakes in the laboratory, you measure the permeability change, and you make the connection between them. If you can calibrate the PZTs, the acoustic emission sensors, to be able to follow that, that's what we're showing here by ball drop. You run the experiments so you measure permeability step changes as a result of the earthquakes that generate them, and you come up with a similar relationship. It's no different from the previous relationship, except that in linking permeability to the cumulative seismic moment, the prefactor, omega, Greek omega in this particular term, is also a function of the seismic moment. So if you factor in the component of the prefactor which relates to the seismic moment, it ends up being that the scaling relationship between these two is not to the power 1, but to the power 2/3. In the left-hand figure, the inclined graphs are showing that relationship to the power 2/3. And the permeabilities that you see in blue are Forge, maybe slightly less than a kilometer in size. Red is EGS, maybe tens of meters, and the dots at the bottom left are centimeter-sized samples, which are all linked together by that relationship. You can explore that on other data sets. I won't go into that because I'm rapidly running out of time. And you can show again that when you look at intermediate data sizes and with other data, you can again make those predictions of behavior, and therefore you can define behavior. So I'll stop there. I merely tried to make the point that because earthquakes result in causing permeability changes, we use them for that purpose, usefully in the crust to be able to generate permeability. Maybe we're able to link the magnitudes of earthquakes directly using techniques that are smarter than us to realize what those correlations are, and then to use data to finally lock those relationships in. So thank you very much for your attention. Oh, perfect. Thank you.
So the next speech will be by Dr. Mehmet Akif Sarikaya, Professor of Quaternary Geology at the Eurasian Institute of Geosciences at the Istanbul Technical University in Turkey.
Hello, everybody. Good afternoon. My name is Mehmet Akif Sarikaya. I am from Istanbul Technical University, and now I'm going to talk about the cosmogenic surface exposure dating applications in various landscapes and landforms. The subject of my talk actually starts here, where you can see a supernova explosion that has been taking for billions of years in the universe. And during these events, there are lots of particles ejected to the space. And we call those as cosmic rays. Although we don't feel them on the surface of Earth, but if you are in the space, there are lots of cosmic rays traveling all around on the space. And they are high energy charged atomic particles originate out of the outer space, and they travel at the speed of light. And when they strike to the Earth's atmosphere, they start to interact with the nucleus of the atmosphere and creating the cosmogenic nuclides. And one of the well-known cosmogenic nuclides is radiocarbon, and we use this radiocarbon to date organic material in the Quaternary. But today, I'm going to talk about those cosmogenic nuclides that is created on the surface of Earth, which we call in situ cosmogenic nuclides. And we use those nuclides to date landforms and understand the process of landscapes and landforms. And there are many applications that we have applied on Earth sciences in the Quaternary time period. Most of the cosmic rays are actually protons, so they are charged atomic particles, and they are affected by the magnetic field of the Earth. And there are some other cosmic ray particles, which are electrons, positrons, and some other subatomic particles. Actually, these reactions create those nuclides. You can see some examples like helium-3, beryllium-10, radiocarbon, neon-21, aluminum-26, and chlorine-36. Those nuclides are produced only in top 5 meters of the Earth's crust. So those cosmic rays cannot penetrate deeper than a couple meters on rock surfaces, but because they have a large mass attenuation. And this method is, as an introduction, is an isotopic method of age determination based on accumulation of those cosmogenic nuclides on the Earth's surfaces. And by measuring the amount of these nuclides on rocks and minerals, we can understand how much or how long these surfaces has been exposed to this cosmic radiation. The accumulation rates of the nuclides are proportional to two things. One is the in situ production, which is defined as P on the right-hand side of this equation. And of course, if this nucleus is a radioactive nucleus, there will be a decay. So the right-hand side has also a lambda n value, which is defines the decay, radioactive decay of this nucleus, if it is a radioactive isotopes. So as you see in this figure, if we measure the concentration of this nucleus on y-axis n, we can measure the amount of time that has been exposed to this radiation, and we can give an age to those surfaces. And you will see some examples of these surfaces in later slides. There are lots of geomorphological applications of cosmogenic nuclide dating techniques, from glaciers to alluvial fans, from fluvial terraces to coastline features, from volcanic features, volcanic lava flows to archaeological settings. So all type of landform processes that has been seen today, we can apply this technique in with some assumptions. The interaction of cosmic rays with the minerals has some certain radioactive production. There are different types of reactions that is occurring on the mineral lattices. The first one is spallation reactions, which have high energy reactions that can split the nucleus and produce the naive isotopes with a smaller mass. For example, oxygen and silica throughout the spallation reactions produce beryllium on top figure here. So if you have silica and oxygen in your rock, let's say there are lots of examples like quartz is one of them and a more obvious one, has been affected by this cosmic radiation, and beryllium has been produced, can be produced throughout these reactions. Chlorine-36 is another cosmogenic isotope which can be produced by calcium, potassium, or chlorine. And as you can see here, calcium and potassium is one of the most abundant elements in rock-forming minerals. There is a depth dependency of the cosmogenic production. Of course, because of these reactions are mass attenuated, on the surface we have the largest reactions. On the left-hand side, you will see the beryllium production through the depth. On the y-axis, you see the depth of the rock. On the surface, there are production of beryllium, but when you go down, there is an exponential decay of production. And up to about 6 meters, there will be almost no production. So the mass of the 6 meter of rock stops this cosmic radiation. So it means that the most of the production on the surface of the rock, and we can either date these rocks by using the accumulation of these nucleids, and also we can also use these nucleids that is accumulated on the surface to understand the surface processes like erosion and uplift and subsidence of the surfaces. On the right-hand side, you will see a little bit different production profile of chlorine-36. Because it has different nuclear reactions, spallation, thermal, and muon absorption reactions, but in total, the red graph shows again the exponential decay of these reactions on the Earth's surface. As you see, there is a 3 meter of attenuation of those nucleids on the surface of Earth. In terms of methodology, of course, first we define what we want to do and then collect samples, bring them to the laboratory to measure the amount of isotopes that has been accumulated on those rocks. And of course, analyzing these rocks has been giving us the age and other processes that we deal with. As an age range, different isotopes has different applicable age ranges depending on their half-lives, of course. But the most applied isotope is beryllium, and it goes up to about a couple of 1 million or more than 1 million years from now to the past. Chlorine-36 has a little bit lower range, but up to about 1 million years can be applied. So during the Quaternary, especially during the late Quaternary, those type of isotopes has been easily applied to the land surface processes. Okay. After this methodological introduction of cosmogenic isotopes, I would like to talk about some examples and field examples and laboratory examples of those techniques. First of all, field sampling. This is the most important part of this method because you need to find a particularly applicable surface and mineral to take samples. On top figure, you can see a moraine which has been deposited by paleoglaciers during the late glacial maximum on the mountains of Turkey, which is nearby Antalya. And those high mountains was supported Quaternary glaciers. Of course, today there is no glaciers on those mountains, but the remnants of glaciers have been protected, as in these pictures, as you see lateral moraines, frontal moraines, terminal moraines, and also because these mountains are karstic features, there's almost no surface water available, so they are very well protected by the fluvial actions. As you see here, crescent-like hills are defined as moraine. As Attila has been collecting samples on top of these crests. For example, here there are large boulders which were deposited by glaciers in the past, and they have been sitting there to us to come to there to collect samples. And again, this is an exposure dating, so the cosmic radiation exposure can be measured on top of these rocks. All you need to collect samples like this on the right lower figure from just on the top of the rocks, about a couple centimeters deep. Chunk of rock has been taken out. Sometimes it is not easy to find those boulders and takes time in the field to find the best place to sample. The largest sample, the sample that has a big root and stable, would be very, very important to take. This video was from Eastern Black Sea Mountains. In Antarctica, there are lots of boulders like this. We know that these are carried by glaciers, and we call it erratic boulders, and well-rounded, big pieces of rocks. The largest one, we sure that these not moved since they are deposited, and it is a good place to measure and collect samples to find out the timing of glacial retreat. Sampling is usually done on the top surface of rocks, a few centimeter deep samples taken by hammer and chisel. And you need to record some information on the field, like the topographic shielding angle, location, thickness, etc., and collect and bring those samples to the laboratory. We have a laboratory in Istanbul Technical University, which is called CosmoLab, Geomorphology and Cosmogenic Liquid Laboratory. Since 2012, we have been collecting, measuring, and publishing different projects. More than 1,000 samples have been prepared. More than 70 papers have been published. We support national, international projects, and we moved a new building in June 2019. And we are open to collaborations, all type of collaborations. If you have a project in your mind in the Mediterranean mountains or in some other places, we are ready for come and take and then make a collaboration with you. We have a very nice, very well productive group. Atilla Çınar is the one, and Dr. Cengiz Yıldırım here again, and Tolga Görüm is here again. I also thank to all to have this collaboration. Without their support, it is not going to be possible to reach this large environment and large support. But we have a really wide applications of cosmogenic isotopes, from surface exposure dating, from retreats of paleoglaciers, erupting time of volcanoes and lava flows, dating landslides and rock avalanches, erosion rate estimates, and fault-related geomorphology, and we have a wide range of applications in many places on Earth. Okay, I would like to give a little bit more detail about the application style of these cosmogenic nuclides. Think about that there is a glacier like this in a mountain environment, and when the glaciers start to retreat because of climate change, those type of boulders has been deposited by glaciers, as you see previously. And these boulders were not exposed. We assume that they were not exposed to cosmic radiation before, and since their deposition, they start to accumulate these cosmogenic nuclides. And when we go to field, take sample, bring to the lab, and measure the amount of cosmogenic nuclides, we can calculate the amount of time that rock has been deposited on its in situ place. The first and the most examples of cosmogenic nuclide dating has been applied to moraines. In this picture, you see a glacier in Swiss Alps. This is Findel glaciers. As you see, glacier has been retreated to some certain position, but before, the glacier was larger. During the late Quaternary, especially during the last glacial maximum, this glacier was much larger. Where do you find this? Because there is two big left and right littoral moraines. As you see in this hotel, there's huge right lateral moraine has been deposited by this glacier. So if you go to field, collect samples, you can find when this glacier starts to retreat or when this moraine has been deposited. Of course, there is an outcome of this methodology because you can understand the paleoclimate of this mountain and because of the change of the climate. So in the field, find out the extent of the paleoglaciers, know the timing of the glaciers by this method, and you can make assumptions or research on paleoclimatology. We apply some modeling, ice thickness modeling by changing the climate regime from today to understand the paleoclimatology, not only by dating the glaciers, but also finding the extent and the modeling of these glaciers. For example, in this scenario, in the Black Sea Mountains, northern Black Sea Mountains, if you decrease the temperature 10 degrees from today, and if you don't change the precipitation regime, you can keep state, you create a glacier domain which has been reached to this extent. And when comparing the extent of glaciers by the modeling and by the field, you can understand the paleoclimatology. And I have a talk tomorrow afternoon about this area. Another example of the application of cosmogenic nucleus is volcanic lava flows, especially for young volcanism, because there is an alternative method to other dating methods, and there is no pre-exposure because magma coming deeply from the earth and it deposited on the surface, and it's an instantaneous deposition on the earth surfaces. So to understand the timing of these type of lava flows, TCN dating can be applied. One example has been done in Kula area in Western Turkey, where Strabo defined or described this land surfaces, this landscape as a burned lands in his famous book in geography. And there are human footprints, one of those ash layers, which was covered by lava flows. And we applied this technique. You can see the footprint of human footprints on the left-hand figure. We applied the cosmogenic exposure dating to lava flows here, and also, in the meantime, we applied the uranium, lead, zircon chronology, and find out similar ages up to about 4.7 plus or minus 0.7 by uranium lead dating. By cosmogenic dating give us 5.1 plus or minus 0.4 thousand years. So 5,000 years ago, there was human which were print their foots. Another example of cosmogenic exposure dating is finding out the bedrock erosion. So apart from the dating, if you have a long enough eroded landscape like Cappadocia region, by collecting samples on top of those or on the places of those chimneys, the erosion rate of those landscape has been researched. For example, here, from right to left, there you can see the evolution of the filled perichimneys. During the plateau stage, the erosion rate is very low, up to about like 0.6, 0.9, 0.5 centimeter per 1,000 years. But when the transition stage and the standalone chimney stage takes account, there will be an erosion rate, bedrock erosion rates, up to about 3 or 4 centimeter per 1,000 years of erosion on the rocks. Another example of cosmogenic isotopes is carbonate denudations, especially in southwestern Turkey, continuation of Alp-Himalaya region. Taurus Mountains has a karstic space where we have lots of erodibility of the landscape. We collected several samples along a transect from Mediterranean coast to the interior region and find out the denudation, the erosion rate of those places has been decreasing from the sea surface to the interior places up to about from 45 to 20 millimeters per 1,000 years to about 7 millimeters and 3 millimeters in the interior. So the dryness of the interior gives the denudation rate lower, but in the Mediterranean coast, where we have lots of precipitation and moisture availability on the surfaces, we have a larger larger denudation rates. And in the below graph, you see the distance from the coast versus the denudation of those landscapes. And again, this is field pictures of those karstic places where we have the denudation. And there are lots of other studies done in Mediterranean places like France, Israel, even in Japan, Antarctica, and Australia, and you see the denudation rates. And on top of this figure, you see Turkey and Slovenia. We have another application on Slovenia to have the denudation rates. The last example of cosmogenic isotopes, of course, active tectonic regions or paleoseismological applications. These are this method either can be applied a fault surface, like this one in this figure. So because these surfaces has been buried before, and when the fault exposed those surfaces, they create the scarps like this by normal faulting or oblique faulting, and these faults exposed to the cosmic radiation, and by measuring the amount of nuclide deposited on the surfaces can be determined by the exposition. This will not give you only the timing of earthquake, but also the slip rate of the faults. So it's very important information. As you see in this picture, the top of the fault has been exposed more than the bottom part because of the karstification, because of the erosion of the surface. Cengiz now taking sample from one of those faults. So this faults not only always like 1 or 2 meters. Sometimes there are more than 10 meters long. So we cut these faults like a ladder, and then collect samples in every about 10 centimeters. And so there are lots of samples to be measured. And the methodology is actually like this. On the right-hand side, you have 2 blocks. During the normal faulting, you expose this red line first. Of course, there are some places where you have this part as a scarp, but also the cosmic radiation penetrates, as I said, 3 meters, 6 meters deep from these rocks. So we have an accumulation on the deepest part of this fault scarp. And the reflectance of this red line on the cosmogenic, in terms of cosmogenic nucleus, is like this. When you go down, there's an exponential decay up to about some point, and also a constant accumulation. Let's say this earthquake happened 12,000 years ago, and if there's another earthquake after about 4,000 years, let's say 8,000 years before now, you have another exposure on the surface, but again, there will be another deepest part of the fault where we have this bumpy shape on the right-hand side. So the previous earthquake exposed this part, the next earthquake exposed this part. If there will be another earthquake, like let's say 4,000 years later, 4,000 years before now, we have a series of, theoretically, we have a series of bumps like this. Each indicates an earthquake. So if we analyze by sampling those and then measuring the cosmogenic isotope ratios accumulation, you have something like this. This data from Italy, but there are similar examples in Turkey as well, starting from 7.2 thousand to 4.9 thousand to 4,000, 3,004, and 1.5. There is not exactly theoretically, but because of the error margins and some unseen geological processes that is occurring on the surfaces, you can analyze the earthquake frequency and also the slip rate of the surfaces. This was sampling directly from the fault surfaces, but there are some examples, other examples, which are measuring or analyzing the surfaces that is related with the faults. For example, this This image, this map is from the eastern central Turkey, which we have a fault, strict slide fault, which cut alluvial fans. And these alluvial fans deposited by floodal action and dated by cosmogenic isotopes. And we find out some surfaces which is cut by fault give us more than 100,000 years, but there are some other surfaces which are not cut by fault, gives us 64,000 years of age. So there's a window gap between this cut and uncut faults. This is another view of this Ecemish fault. As you see, this old surface is here, but the younger surfaces has not been cut by the fault. And again, this is another profile of, in the figure. You can apply this technique by the fault-related activities in different places. And the surface sampling and also on the deep, when you dig a hole like this, you can collect isotopes profile and then understand the timing of the fault if you don't find large boulders on the surfaces. Thank you very much for your attention.
So the last speech will be by Mr. Andreas Matsarakis, former director of the Research Center for Human Biometeorology at the German Meteorological Service and professor at the Albert Ludwig University of Freiburg in Germany.
Thank you very much. Ladies and gentlemen, my background is meteorology, so you can see that here I'm well prepared. I cannot promise you something about the weather today, but I mutated very early after my study in meteorology, in biometeorology. That means I'm also prepared here, and this is the reason because I will talk about heat. Good. I think most of you cannot understand, maybe you're not familiar with the term heat management. And this is exactly the reason because I would like to talk today about heat management. And I have a second affiliation, and my second affiliation is at the Democritus University in Thrace, which I'm also a member there. And the reason because I want to talk about heat, especially heat management, and I would like to ask you, can you please recap about this summer if you have been exposed in heat? How many times? And what about your neighbors? What about your family members who are, let me say, in my age? I'm 65, maybe also older. That means when we talk about heat management, we have to think further. And what we see, especially here, is that when we talk about, when we refer to climate change, we realize that climate change has a very important effect on a specific topic, which is human health. And this topic, human health, it's not only, let me say, the medical sector, but we have many, many other sectors which are interconnected. And when we talk about the effect of climate change on human health, we realize that we don't have only direct effects, that means something like heat stroke, but we have also some indirect effects. And if you look about that, especially when we realize about the effects, and I'm referring not only to heat, that in reality, we have to realize that there are no organs that we have in the human body who are not affected. That means we have a general effect, but also a specific effect. And the reason why I want to talk about heat is mostly when we talk about heat, we think about temperature. But in reality, there are many, many other factors, especially from the meteorological side or the atmospheric side, which have to be included, like humidity, radiation, wind speed, but we need also some other factors. And then when we transfer this information, let me say, to the world population, we know exactly at the moment that more of 50–60% of the world population is exposed to heat. And the second part is that most of the people live in urban areas. That means at the moment we have more than 50% also of people who are living in urban areas. And then we have also some additional risk factors like age, like social status, but also in general the health status. In reality, we are talking about quality of life. And most of the people, when we talk about the effect of heat on human health, we think mostly on mortality. But in reality, it starts much earlier, like the morbidity, but also the productivity, the loss of the productivity. And this is exactly what we want to know. And we know that, let me say, the issue of heat is not an issue, let me say, for the future, but we are still experience when we take the Mediterranean since the 80s, in some cases also earlier, but also, let me say, in the northern part of the Mediterranean, maybe also in the northern part. And concerning heat, there are huge knowledge about the effect of heat. And we have also a good knowledge about what to do, what measures to take, and what actions to take. And then, when we talk about heat, in reality, it's not only a meteorological factor, it's not only the definition of a heat wave or extreme heat, but we have to consider much more factors. Not only the meteorological factors, also air pollution, or the pollen that we have in the air, or fires, or forest fires that we have, and so on. This is a complex issue, but we in reality can deal with about that. On the global level, let me say also in the international level, we know and we have realized, especially the governments and administration have realized, and the international organizations, especially G7 or G20, that is an issue. They run, let me say, analysis about that. Also the huge funding organization like Rockefeller or Wellcome Trust, they are funding projects in a specific target. At the moment, and we have a very fantastic organization with this, the Global Heat Health Information Network, under the umbrella of the WHO and the WMO, the World Meteorological Organization. They put focus not only on urban heat, because we are exposed, of course, in urban areas, but also about the mental health, but also about the events. Please think about the events like the FIFA that we had some years ago, or summer games or summer events which has to be canceled and so on, but finally also about indoor heat. And it's not a secret. Indoor heat is maybe the most important concerning summer. Not every part in the world has the possibility with air conditioning. Maybe in some cases it's too expensive. And then we have also, let me say, the maternal and child health, which is at the moment, let me say, the topic of interest. And the question now is how to quantify that. Is there a possibility, is there a methodology or approach in order to quantify that? Because we are not only exposed in cold we can adapt, but in heat it's difficult to adapt. And we have all these possibilities how to quantify that. And we have combined here several approaches, and one of the first approach that we have is the thermophysiological one, because the human body has the possibility to react. There are mechanisms which can start for a specific situation and so on. The second one is the energetic aspect, because we have something like a magical number in biometeorology, which is 37, which is the core temperature of the human body, and we need exactly that in order to quantify. Of course, we have additional factors, the skin temperature, sweating, and so on, and we have the possibility, based on the energy balance or on the heat budget of the humans to analyze that, and we have the possibility to judge that based on classes, on scales of thermal perception, and so on. And based on that, we can analyze that, and the methodology provides us a possibility where we take not only air temperature, but also humidity, wind, radiation, also thermophysiology in terms of activity and clothing, and from there we can extract a thermal index, something like a real field temperature. And this is the basis that we have at the moment in order to bring this information, I mean biometeorology, together with epidemiology, mortality or morbidity studies. And we have several of these indices. At the moment, we have 5 of these indices. They are well represented and described in guidelines. One of these guidelines here is this guideline from Germany, but we have also international guidelines in this context. And one of these most known indices that we have is the physiologically equivalent temperature. And here we have the possibility to describe that. And this provides us a possibility that means here in a room, at the moment, you can judge something about 20 to 23, but when you go outside with 20 centigrade, you have a different perception because of different wind and different radiation. And this we can bring together with mortality data in order to provide, let me say, thresholds. That means when we have a situation which means danger for humans and so on, we have the possibility to describe that. And concerning the future, or concerning the situation that we have at the moment, there have been developed heat health action plans, and I'm referring not on heat action plans, I'm referring on heat health action plans. That has to be really specified and so on. And we know concerning to the future that in terms of extreme heat, but also heat waves, we will have an increase in the intensity, an increase in the amount, but also an increase on the duration. And the duration is that thing that scares me especially, and so on. And in the heat health action plans, we have several core elements, let me say also factors, and the first of them is the coordination and cooperation. In reality is who is responsible for actions and measures when we have heat. The second one is the accurate and with thresholds which are regionally specified heat health warning system. And then we have the possibility of information and communication. And then, as I mentioned before, is the indoor situation, because we have several studies which are showing us that the indoor conditions are more important, especially the nocturnal situation. And then we have the vulnerable groups. It's a funny story that I would like to mention. There was a study which found out that most of the people, more than 50% of the people, don't know that they belong to a risk group. And my comment was, after 3 days of exposure in heat, every one of us belongs to a risk group. And then we have the preparedness of the health and social care sector, which is one of the most important ones that we have. And then we have the long-term context, which is the urban planning and the construction. And finally, is the monitoring and evaluation of all the actions. That means we need a good, appropriate planning, not during the summer, but before also the summer. We need information and preparation for the acute situation during extreme heat wave, but we need also post-processing, analyzing what happened last summer. This was also my question, why we have to recap about the situation of last summer. And heat is an all-year issue. It's not only during summer because of the preparation, because of the update of the heat health action plans and so on. I would like to provide you some information about some parts of some of the key elements in the heat health action. The plans, the first one is the heat health warning system. I have 2 examples, and I would like to go more in detail about the development and the release of warnings. The first example is from Germany. I was, as mentioned before, I was leading the research center in Germany about the warnings and so on. We have the weather forecast, we have the combination with the methodology I showed you before, and then we have specific thresholds based on these thermal indices I show, and then we know that the first heat wave is the most crazy one, because we are not adapted. And this we combine in terms of a real field temperature, and we combine also, based on the weather forecast, the conditions in the indoors. It's a model which is running. We get the warning proposal. This is verified by the group who is responsible about that, and then we release the warnings for the counties, because we have to consider the administration level. In Germany, this is the counties. In other areas, maybe it's the states or governmental areas and so on. And then we have the release of the warnings, first of all, of course, for the authorities, and then for nursing homes, but also for the public. And finally, we have to consider also elderly people, because they are more exposed in heat, and then also the people who are living in cities. And this has to be communicated by different ways. And since some years, there's a possibility to take action, not only to take actions, but to take the warnings as the starting point in order to take actions. This is an example from Berlin. We have different disseminators, recipients, and we have tailored action plans for the specific sectors which are interested. And then we have the possibility also for, let me say, easy, understandable communication. This is an example from the Ministry of Health in Germany that was 2023, and they provide a simple information, measures that can be really applied very quickly, and it starts as a starting point. Everyone has to register for the heat warnings, and then providing actions like drinking water, keep indoors cool, stay in shade, avoid activities, light food, and of course, take care about others. Maybe this is the most effective one. Based on the heat health warning system in Germany, in Athens there have been a further development in that, where we included a thermal index which is more advanced, considering male and female adults, seniors and workers, but also considering adaptive mechanisms. And this is maybe the future for the heat health warning systems. And we have here, of course, a possibility in order to provide information, to provide measures based on different criteria, but also levels of measures. And another success factor is indoor. We have developed in Freiburg, so low-cost sensors. It's not so expensive. They include also temperature, humidity, wind speed, and also radiation. And we have the possibility to check the situation in order, not only in order to know how much is the heat in indoors, but also to validate the warning system. And we see a huge variability. The left side graph, you see the yellow one is in the basement of the building. The building is about 10 floors. And then you see that you have a huge variability also in the building, but you have also a huge variability indoors, also in the different orientations of that. And one of the main factors that we need in the future, or at the moment we need this also, is about the medical centers, university hospitals, in order to quantify the building characteristics such as air conditioning effects or the year of construction, but also the exposition in the floor. This is an example from 2023 where we equipped the university hospital in Germany, in Freiburg, with 65 sensors and so on. And then we have the factor number 7. This is the long-term factor, and here we have the combination of different approaches, of different possibilities how to analyze that, and we take here all these things that we know about urban vegetation, that means blue and green strategies, but we include also artificial or anthropogenic modifications like the materials and water misting systems, how we can make the situation, especially in the macro scale, I mean outdoor in urban areas, more quantified. I have another example for you, which is from Freiburg. In Freiburg, you see in the first picture that you see in the upper left side, that was something like a green area or grass area which wanted to be transformed to a multifunctional space. Of course, people don't like that. Finally, it has been transformed. but we make an analysis, what is the effect if we remove only one tree? The tree was not so big. It was only close to the bus station, but the bus station has to be disappear. And we find out that removing only one tree, the amount of hours with heat stress will increase from 205 to 330. That means 125 hours. Only to mention, if you want to know what is the effect between the differences between sun and shade, if you go to the temperature between, let me say, a tree, it's 1 centigrade, the maximum in a forest is 3 centigrade, but if you take a thermal index, what the people feel, it can be 10 to 15. That is what we feel. We don't have sensors for air temperature and so on. And then we have cross-sectoral factors, and here we are in the topic of communication, the way how we communicate, but also how to implement all the knowledge that we have, let me say, in administration, in guidelines, and so on. But in order to do that, first of all, especially for heat, we need a common language. This is a picture from the urban planning department of the responsible person there, and they talk about shade, meteorologists talk about radiation, they talk about ventilation, meteorologists talk about urban roughness. That means we need a common language. And then maybe we have to change a little our perspective from scientific side, and this is the actions that we have during heat, or we can have, and this not only having information about temperature, about if it's a warning at the moment, but also the distance to the next hospital, the distance to the next pharmacy, to the next park, and so on. This is my last presentation, my last transparency. This picture is taken in Peloponnese 2 months ago in Amaliada, and you see the pigeons here, they behave right. Thank you very much.
Okay, so that the speeches now are finished, you are welcome to join the coffee and lunch break at the east yard of the building. Thank you.